The objective of this lab is to demonstrate squareness of motion measurements. Specifically, we will measure the angle between the two axes of motion on this ultra-precision lathe or diamond turning machine. In this diamond turning machine, or DTM, the hydrostatic bearing slides or carriages are configured in a T-shape. The rotating spindle and workpiece ride on the Z-axis slide, while the diamond cutting tool rides on the X-axis slide. By coordinating the relative motions of the tool and workpiece, flat, spherical, and aspherical surfaces of revolution can be generated. As seen in this illustration, the tool engages the workpiece at the horizontal centerline of the spindle. Therefore, the squareness of motion of the axes in that horizontal plane is the unknown to be determined. The squareness measurement is actually the determination of the angle between the mean lines of each axis of motion. That is, for each axis, a set of data points is collected which represents the straightness of motion of that axis with respect to a reference straight edge. In our lab today, we will measure the straightness of motion with a capacitance gauge and a metal-plated zero-dur straight edge. In this lab, sign convention is critical. From our previous work with the cap gauge, we know that a decrease in the separation of the straight edge and the cap gauge results in an increase in signal voltage. Notice that in the setup for the x-axis straightness measurement, an increase in voltage corresponds to a positive z-axis error in the motion of the x-axis slide. In the setup for the z-axis straightness measurement, a decrease in the separation of the straight edge and the cap gauge again results in an increase in signal voltage. However, in the setup of the z-axis straightness measurement, an increase in voltage corresponds to a negative x-axis error in the motion of the z-axis slide. The best fit lines for each set of data are generated, and the angles of those mean lines with respect to their abscissas are calculated. The angle between the two mean axes of motion can then be determined using the two angles θ1 and θ2. In this case, given the T configuration of the slides, the nominal angle between the axes is obviously 90 degrees. If the two setups of the reference straight edge were precisely orthogonal, the 90-degree interval between the two setups would be the reference, and phi, the actual angle between the two axes of motion, would be equal to 90 degrees minus θ1 plus θ2. The significance of this squareness error is shown in this illustration. In this DTM, the coordinate system used for programming the tool and workpiece positions is based on the premise that the two axes of motion are orthogonal. Let's assume that the center line of the spindle and workpiece coincides with the z-axis, and that the origin of our coordinate system lies at the center of the workpiece surface. At the origin, the squareness error has no effect on the tool position. However, as the tool moves away from the origin, not only the tool's x-axis position changes, but the tool's z-axis position also changes. Since a programmed x-axis position change also produces a z-axis position change, position error has been introduced. The z-axis position error is the product of the sine of the squareness error angle and the programmed x-axis position. Notice that the squareness error also produces an x-axis position error. However, the x-axis error component equals the programmed x-axis position times the quantity of 1 minus the cosine of the squareness error angle. Since the cosine of a very small angle is nearly 1, the x-axis position error is negligible for small angles and moderate values of programmed x-axis positions. Consider this example. If the actual angle varied from 90 degrees by 1 arc second, an x-axis position of 100 millimeters would be accompanied by 485 nanometers of z-axis position error. For comparison, the x-axis position error would be only 1 picometer. Again, this is because the z-axis error is the product of the programmed x position and the sine of the squareness error angle, while the x-axis error is the programmed x position minus the product of the programmed x position and the cosine of the squareness error angle. As illustrated here, non-squareness of the axes of motion can undermine the positioning accuracy of the tool relative to the workpiece. Fortunately, today's high-speed computer processors can facilitate error correction techniques which can compensate for these types of machine errors. However, accurate measurement of the error values and the repeatability of those errors is necessary before any error correction schemes can be implemented. The procedure for this measurement is quite straightforward. A single straightness of motion trace is taken for the x-axis as the cap gauge and the x-axis slide are moved past the straight edge mounted to the stationary z-axis slide. A precision index is used to rotate the reference straight edge precisely 90 degrees to facilitate the z-axis straightness of motion measurement. A single z-axis straightness of motion trace is taken as the straight edge and the z-axis slide are moved past the cap gauge mounted to the stationary x-axis slide. Using a least squares method, the mean straightness line is found for the x-axis of motion. Next, theta 1, the angle of the mean straightness line, is calculated. The mean straightness line for the z-axis of motion is determined. Then theta 2, the angle of the mean straightness line for the z-axis trace, is calculated. The two angles theta 1 and theta 2 are inserted into the equation shown to determine phi, the angle between the two mean axes of motion. In neither step will the straightness error of the straight edge be removed from the measured data. However, if the magnitude of the straight edge error is significant, the validity of the squareness measurement can be jeopardized. In today's lab, we will ignore the errors in the straight edge. In setting up for this measurement, a precision index is mounted to one slide, in this case the z-axis slide. Here the spindle chuck has been removed and the index platform is being attached to the spindle housing on the z-axis slide. Since the squareness measurement is made in the cutting plane, that is, at the spindle center line and tool height, the platform is positioned so that the straight edge center line will be located as close as possible to that height. Efforts are also made to horizontally align the platform with the x and z axes. This is done in an attempt to keep the probe orthogonal to the straight edge during both steps of the measurement, as well as to minimize path differences along the straight edge between steps 1 and 2. The averaging nature of the capacitance gauge also reduces the effects of path differences. An electronic indicator gauge is used to bring the platform into alignment. The index is mounted on the platform and the position is zeroed. A kinematic cradle was constructed to support the straight edge with maximum positioning repeatability during the reversal process used for straightness of motion measurements. Although the straight edge won't be repositioned between the steps in this squareness measurement, we will use the cradle for supporting the straight edge. The kinematic cradle is attached to the index so that it is nominally parallel to the x-axis. As you recall from a previous lab, Zero-Dur is a glass material with a very low coefficient of thermal expansion, making it a very attractive material for high-precision applications requiring dimensional stability. The reference surface of the straight edge has been ground, lapped, and polished to be both smooth and flat. The error in the straight edge is specified as 45 nanometers over the 300 millimeters of length. The reference surface has been metal plated to facilitate use with a capacitance gauge. The optical straight edge is carefully placed in the cradle. The capacitance gauge is mounted to the x-axis slide such that it probes the reference surface of the straight edge. The capacitance gauge will measure the lateral motion error of the moving slide and the irregularities in the reference surface. As you recall, the non-contacting probe will sense changes in the separation of the probe tip and the reference surface by measuring the changes in the capacitance of the target area on the reference surface and the sensing area of the probe. The separation changes can be read from the analog display, or as we will demonstrate in this experiment, can be recorded as analog signal voltages. The signal voltage range is plus or minus 10 volts. At 2.5 micrometers per volt, this equates to a measurement range of 50 micrometers, which is more than adequate for our experiment. The analog voltage signal from the capacitance gauge will be sent to an analog input on the diamond turning machine's controller. Inside the DTM controller, the analog signal will be converted to digital values. The DTM controller, which has resident data gathering routines, will record the X and Z axis positions and the digital signal voltages. Later, these voltages will be converted to distances using the scaling factor of 2.5 micrometers per volt. Recall also that a decrease in the separation results in the display needle moving to the right of this display's center, and that the output signal voltage becomes a more positive value. An increase in the separation results in the display needle moving to the left of center, and the output signal becomes a more negative value. Before measurement can begin, the straight edge must be brought to an orientation which is parallel to the x-axis of motion. To begin this procedure, the x-axis slide is moved until the cap gauge probe is approximately positioned at the center of the precision index. The separation of the cap gauge probe and the straight edge is adjusted until the console reading is within the plus or minus 0.001 inch range of the cap gauge. Using a combination of physical positioning and electronic zeroing, the meter needle is brought to mid-range position. Next, the x-axis slide is jogged so that the cap gauge probe is traversed along the straight edge away from the center of the index. The change in the separation of the probe and straight edge is monitored as the probe traverses until the cap gauge reading goes off scale or the x-axis end of travel is reached. The angular position of the straight edge is adjusted using the angular fine adjustment on the precision index. This fine adjustment consists of two opposing fine-pitch screws which deflect a paddle attached to the bottom half of the index. Depending on the sign of the change in the separation of the probe and the straight edge, one of the screws is withdrawn and the other screw is advanced, thereby causing a deflection of the paddle and a small angular change in the position of the index. The angular position of the index is fine adjusted until the original probe straight edge separation is obtained. Note that the simplicity of this adjustment was made possible by originally positioning the probe in the center of the index. Since the first cap gauge reading was made with the probe at the approximate center of the straight edge rotation, that first reading will be nearly constant since it will be essentially unaffected by the rotation of the straight edge. Therefore, if the straight edge is rotated so that the reading at the second point equals the reading at the first point, by definition, that straight edge must be parallel to